Hi there, I'm Dennis, and this here is the rehearsal of my PhD thesis defense, which will go live on YouTube approximately at the same time as I'll have my actual PhD thesis defense. So the main reason behind this video was to do a simple practice run of the presentation before the actual date itself. But I also hope that the presentation itself, that hopefully can inspire other people in how a PhD defense might be able to be structured, or presentations in general could potentially be structured. So I did my PhD in the computer vision and graphics group at the University of Basel under the supervision of Professor Thomas Vetter, who is the professor famous for the Basel face model, which I've featured in another video here on my channel earlier. So talking with a lot of PhD students, postdocs, professors over the years, I found that there is a universal standard for how a PhD defense is structured. So most likely the setting I'm in will be much different, in fact, than the one you will be facing. At the Computer Science and Mathematics department in Basel, the standard setting is that the defense is public to everyone. And so I find it quite nice when the speaker devote quite some of the presentation itself to the general public, so it's a bit more accessible to everyone. For my defense, I have 30 minutes to present my work, followed by 30-minute questions, which will be a mixture of questions from the committee, plus possible questions from the general public. So as you can hear, with time being so limited, you really have to cut away everything possible that is not absolutely necessary to get your message across. So the current version, you'll see, it took me quite iterations already to get to this point. I'm sure if I had more time, I would iterate more and improve several more aspects of the talk itself. And so now, without further delay, let's get into my approximate 30-minute presentation. Hi everyone, and welcome to this presentation where I'll introduce you to some of the findings done in my PhD thesis titled A Probabilistic Surface Registration Framework with Applications to Partial Data Analysis. In this talk, we'll be focusing on probabilistic non-rigid registration, why we need it, what it is, and as already hinted in the title, where it is useful. But let us start this presentation in the mountains here in Switzerland, at a crime scene, where the police has just found some evidence in form of skeletal remains. More precisely, a partial femur bone from a human. From a human bone, a lot of interesting properties can be identified about the person. If we, for instance, know the length of the femur, we can get an estimate about the height of the person and then cross-validate that with a missing person database. So the police brings back the femur to the forensics team, who makes a digital scan of the bone. They can then perform a comparison of the femur with a full database of other femurs. But instead of finding the most similar femur in the database, they might be using the statistics from all the femurs in the database. This could be done in the form of a point distribution model. A point distribution model simply describes the mean and the variation in a dataset. What the model let us do is finding a linear combination of items from the database that best describes the data. So with this model, we can now compute an estimate of the complete femur from where we can infer the height of the person. The point here from point distribution model refers to the surface representation, which is represented as a simple point set. Now, this here leads us directly to one of the underlying principles that point distribution models rely on, which is point correspondence. Point correspondence is the process of identifying points with the same anatomical meaning and location across multiple items. So in this case here, across discrete surfaces. So now if I ask you to identify this point on the partial femur, you might choose this point here. And let us try to locate another point in the known area of the femur. It is also very important here to know which areas from the model that do not have any corresponding points. And so the point here around the knee, we're very sure that it is missing. But what about the points on the shaft? The shaft of the femur is a large smooth area without anatomically stable points that are easy to identify. And so the corresponding point here could be this one, or it could be that one, or maybe this one. Why is this now a problem, you might ask? Well, different correspondences directly lead to different surface completions. So by using one of the yellow correspondent pairs on the previous slide, we might end up with this bone. But we could also end up with a bone that is slightly longer or slightly shorter. And so the main takeaway from this is that no single best reconstruction exists, but instead a complete distribution of different correspondent pairs exists. This process here of automatically establishing point correspondence between surfaces by deforming one surface is what is known as non-rigid registration. And so with probabilistic non-rigid registration, which we introduce in the thesis, we're estimating the full distribution of possible correspondent pairs. So from this distribution, we can look at the variability of each area and see that places that are found in the partial femur has a very low variance, whereas points in the unknown area of the femur has a very high variance. Interesting enough, we can also see that there's even a lot of uncertainty in the crossover area between the known and the unknown part. Before going into depth with probabilistic registration, let us first have a look at some of the contributions from this thesis. At ECCV 2020, we introduced a special version of our probabilistic registration framework. We now also have a paper available in preprint which introduced Ginger as a generalization of existing non-rigid registration algorithms. In this thesis, we extended the concept from these two papers and called it P-Ginger. This is the main contribution that I'll also be talking about today. In the thesis, we also go over different applications of P-Ginger. Here I'm just highlighting the ones that we have individual papers published about, such as our 2018 CVPR paper, our MICAI workshop paper from 2019, and another MICAI workshop paper from 2020, which we'll briefly touch upon in the end of this talk. But before introducing P-Ginger, we'll first introduce Gaussian process morphable models, which is an essential part of P-Ginger. So Gaussian process morphable models is a generalization of the standard point distribution model, which I introduced before. So for a point distribution model, the deformations that a surface can undergo, they are learned from data. In a Gaussian process morphable models, it also allows us to analytically define these deformations in form of a kernel function. We will later on look at popular choices for such kernel functions. The kernel function is then approximated, and the deformation can be controlled with an alpha vector. From this, we can visually inspect the deformations that the model can undergo by randomly setting this alpha vector. Another reason than having analytically defined deformations to use Gaussian processes is how we can update the model based on observations. This is done using Gaussian process regression. So let us now say that we observe where the location of the femur head should be, and we additionally assign some uncertainty to this observation. We can now compute the closed form posterior distribution, which again is a Gaussian process morphable model. The mean of the model has been updated, and by sampling from the model, we see that the observational point is stable relative to this uncertainty that we have assigned to the deformation. If we instead of 1 point condition on 6 different deformations, we again get a posterior model which takes all these 6 observations into account. With a deformation model defined in form of a Gaussian process morphable model, let's now look at non-rigid registration. So given a target surface, what we're interested in is finding the alpha vector, which best describes the target surface gamma t. And so the optimization could look something like this here. And what we see here is that the model takes iterative steps to get closer and closer to the target. We then end up with a synthesized version of the target surface, which is the one we use for further analysis. So non-rigid registration can also be seen as wrapping a reference surface around the target, according to some deformations defined on this reference surface. The optimization is done by minimizing the distance between the target and the surface described by the alpha parameter, noted by here. Usually there will also be some regularization involved, controlled by a Haber parameter, which makes sure that the deformations that we end up with, they are smooth. This setting here is what we'll refer to as the traditional setting. In probabilistic non-rigid registration, we're not optimizing for a single best alpha parameter, but instead we're interested in the distribution of alpha parameters given a target surface. And in our setting, we're not computing the closed form posterior model, but instead approximating it with an MCMC method. It should be noted here that the alpha vector, it follows a multivariate normal distribution, a standard multivariate normal distribution, so it's easy to compute the probability for each alpha vector. And the likelihood function here is used to evaluate the distance between the target and the surface described by alpha. So let us now look at how probabilistic registration can be done using our framework P-Ginger. So P-Ginger just stands for a probabilistic version of Ginger, and the Ginger acronym covers over a method that iteratively uses Gaussian process regression for registration. At the core of P-Ginger, together with a Gaussian process model, we have the Metropolis-Hastings algorithm. So the Metropolis-Hastings algorithm is a Markov chain Monte Carlo method for obtaining a sequence of random samples from a probability distribution. And it works by we first initialize the alpha vector, then a new alpha sample is proposed. In the standard setting of Metropolis-Hastings, this is most often done using a random walk proposal. So we randomly try setting the alpha vector. Then we have a validation step to either accept the new sample or keep the old one for the next iteration, alpha 1. This then continues to alpha 2, alpha 100, the 100th iteration, and all the way up to infinity. If we now lay out all these samples, this is what is known as the Markov chain. And from the Markov chain, we can discard the first samples, as this is where the algorithm is initializing, also known as the burn-in phase. The samples after the burn-in phase is the samples from our posterior distribution, which we are interested in. And as hinted here by alpha infinity, it can take a very, very long time to estimate the distribution using a simple random walk proposal. So what we do different with P-Ginger is to use a specially designed correspondence proposal. So let us now look at how one step of P-Ginger looks like in comparison to this random walk proposal. As mentioned on the previous slide, we initialized the alpha vector, and on this slide here we also show the prediction of the 3D instance. Let's also visualize the target surface. The first thing to do is then to estimate the correspondence between the two surfaces. This could be done purely manual from expert annotations, and we'll also shortly look at popular choices for this correspondence estimation function. So each observation also comes with a correspondence uncertainty which needs to be set. Then the posterior distribution is computed using Gaussian process regression. And we then take a random sample from the analytic posterior model, and we use this as the proposal for the Metropolis-Hastings algorithm. Finally, we decide if the sample should be accepted or rejected, as also shown on the previous slide. And so if the sample is accepted, the gray surface is now updated to the blue surface. Now you might ask, if this is P-Ginger, what is GingerGen? Well, the main difference is that Ginger takes deterministic steps, and so instead of taking a random sample from the posterior model, we use the posterior mean in Ginger. And additionally, we also do not evaluate if the sample should be accepted or rejected, but it's always accepted. What we see now is that both pGinger and Ginger relies on some common properties, which it turned out that a lot of existing algorithms published in the last 20 years implicitly follows as well. And so by describing existing algorithms in the Ginger framework, we can directly make them probabilistic in comparison to their deterministic nature. The three properties that are referred to are a kernel function for the Gaussian process multiple model, a correspondence estimation function, and some uncertainty given to this correspondence estimation. So by explicitly defining these three properties, we're able to compare a range of existing non-rigid registration algorithms. So here we'll just look at three different methods. The first one being coherent point drift. And then we'll look at two different ICP methods from the optimal step paper under our Ginger framework. So our goal now is, in other words, to fill out the empty cells in this table. And we'll do so by starting out with the correspondence estimation function. On this slide, we fix the deformation model and look at the correspondence estimation function only. So now yellow is the target, the transparent one we see is the model, the initialization of the alpha vector. And for the ICP method, it's straightforward, as simple closest point are computed as being the estimated correspondences in each step. We can also look at how the surface is getting closer and closer to the target if we run the registration here. And we can see how the vectors become smaller and smaller the closer we get to the target. The more interesting finding here is with CPD, which by converting CPD into the Ginger framework, we can directly identify how this estimated correspondence in each iteration look like. So in CPD compute a weighted average of each point from the model corresponding to all the other points on the target surface. And so in the beginning, these deformations are not located on the target surface because the weighting is more or less equal on all the points on the target. And if we try to visualize how this looks like, then we see that the model somehow shrinks first before expanding and slowly fitting to the target. So in the ICP paper, the correspondence function was explicitly stated, whereas it was only implicitly mentioned in the CPD paper. But by comparing the two algorithms in Ginger, we can see how this here is kind of fundamental difference between the two algorithms, how they operate. Let us now turn to the deformation models, which are defined by a kernel function. For better visualization here, we use an armadillo in this example. We're showing the absolute covariance between points on the armadillo and a point here on the foot. The first kernel that is shown is the Gaussian kernel. And using a Gaussian kernel, point correlation is computed based on their Euclidean distance between each other. So by putting the armadillo here in another pose and recomputing the distances, we see that the point correlation changes. The Gaussian kernel is what is used in the CPD algorithm. An alternative kernel is one that uses a surface distance measure. And so if the kernel is computed based on the armadillo in another pose, the correlation stays the same. The kernel shown here is a generalized inverse Laplacian kernel. This is what is used in the ICP-T method. The last kernel also uses a surface distance measure, but we additionally see that points that are located opposite of each other have a high absolute correlation value. This is due to an added dot product kernel in comparison to ICP-T. So here it should be noted that for the CPD method, the kernel is explicitly mentioned in the paper. In the ICP paper, the kernel function only implicitly given in form of the regularization in a minimization problem. And so going back to the table, we can now insert our findings. The three methods uses three different kernels, so Gaussian, the generalized inverse Laplacian or the generalized inverse Laplacian and a dot product kernel. CPD uses a somehow probabilistic way of finding correspondence in each iteration, whereas ICP uses a simple closest point heuristic to do so. Additionally, it should also be mentioned that CPD has an automatic way to update the correspondence uncertainty in each iteration, and the uncertainty is additionally performed for each correspondent vector independently. The ICP method, on the other hand, uses a hyperparameter to manually configure the uncertainty, which is then the same for all correspondent pairs. So besides directly comparing algorithms based on these three properties, we can now also create new novel methods based on mixtures of properties here. This could, for instance, be a CPD method that uses a Laplacian-based kernel. Now it might be interesting to look at how Ginger and pGinger directly compares. So we did a FEMA registration experiment where we took the map estimate from pGinger and the final value from Ginger and compared the registration performance. This was done on 50 targets with 100 random initialization of the alpha vector. So what we see is a total of 5,000 registrations. And the comparison here should really be done on a per method basis between Ginger and pGinger. So we can compare ICP under the two methods or CPD under the two methods. And what we see is that the probabilistic method on average give a better map estimate. But the main benefit of our probabilistic framework pGinger is not the improved map solution. It is instead on the posterior distribution. So when registering a target, we can, for instance, visualize the sum of independent point variance from the distribution. Likewise, we can also look at the variance only in the direction of the surface normals and see that there is close to zero variance in this case. So from this, we can infer that the uncertainty in the shaft region here, the main variability that is found there is a shift in the correspondence of the surface itself. And so if we turn back to our crime scene, with traditional methods, the bone length estimate is highly dependent on the correspondence that is used. The red dotted line in the plot shows the ground truth bone length. And so we can see that if we use the ground truth correspondence, we can predict the correct length very well. Unfortunately, this correspondence is not available to us in a real world scenario. We can instead use pGinger to compute the posterior of correspondences. From there, we can extract measures which are not dependent on a single correspondence estimate and see that the ground truth is a likely instance under this full distribution. But more importantly, we can narrow down our search in the missing person database based on a confidence interval. In the thesis, we have shown several different applications of pGinger. We already discussed the posterior estimation of partial FEMA surfaces. Another dataset we worked with was faces. These two applications here can be seen as analyzing partial data using statistical models. Additionally, we also explored how statistical models can be built from different settings of partial data. We both worked on statistic hand examples, how teeth datasets with different properties can be merged, or how a combined face-skull model can be constructed. So let us now look at how statistical models can be constructed from partial data. For simplicity of this talk, let us keep to the themes. And what we see here is a dataset consisting of purely partial data. Now we just need one complete surface on which we analytically define our deformation model. And then we can use pGinger to obtain the posterior distribution of registrations for each of these 10 targets. Now if we zoom in on one of the femurs, we can see how the completions might look like. So in red, we have the partial data. In orange is the ground truth shape. From the posterior distributions, we can extract the map estimate for this one case here. We can also compute the mean of of a lot of the random samples from the distribution. Or we could directly look at different samples from the posterior distribution. What we'll now do is to compare models that are constructed from either the map, the mean, or random samples from each of these 10 distributions. On a minor side note here, the statistical models, the point distribution models that we are computing, are computed using principal component analysis on a data set in correspondence. And so to evaluate which method works the best for constructing statistical models, we use two different measures. The first measure is generalization, which measures how good the model is in describing previously unseen data. The dotted line here describes the maximum number of principal components for most of the methods. As we only have a dataset of 10 females, we get a maximum of 9 principal components. We see that both the map, the mean, and the model constructed from one random sample from the distributions, from all of these 10 distributions, have more or less the same generalization score. But by computing the statistical models from 5 or even 100 samples from each of the distributions, the model is able to generalize much better. The other measure is specificity. While we want the model to generalize to novel data, it should also stay within its shape space. And so specificity measures how far random samples from the models are from their training data. Here we see that the mean is better than the map solution. And also a lot better than taking one random sample from each of the distributions. But by using 5 or even 100 random samples, we have a specificity measure that is as good or even better than the mean. And important to note here is that this is while also generalizing better to new data. So finally, let us conclude by summarizing the main points from this talk. One of the main problems in traditional non-rigid registration is the underlying correspondence assumption. Instead, we formulate probabilistic registration as estimating the distribution of surfaces given a target surface. Our method to implement this is pGinger, which uses the metropolization algorithm to propose new samples from the posterior distribution. The usage of a specially designed correspondence proposal makes it possible to take informed steps in comparison to a random walk proposal. From the distribution of registrations, we can extract the registration uncertainty. And with the formulation of Ginger, we have shown new novel insights into existing algorithms, such as the correspondence estimation in CPD and the implicit usage of a dot product kernel in some ICP methods. Finally, we also showed how pGinger can be used to create point distribution models from purely partial data. And on that note, I would like to thank you for your attention.